Okay, in this video, we'll take a look at our first example of magnetic force on a charged particle. Our formula for magnetic force on a charged particle, the force is a vector, so it's a vector quantity. It's the charge that has the force upon it multiplied by the velocity the charge is moving at, cross product with the magnetic field within which the space that the charge is moving. So that gives us our vector formula. Our magnitude formula, the cross product yields a sine phi, where in this case our phi is labeled here as theta, so we'll change that to phi. Our phi is the angle, the short angle between the velocity vector and the magnetic field vector. And when we're just finding the magnitude of the magnetic force, then we use the magnitude of the charge, or the absolute value of the charge, the speed times the magnitude of the magnetic field, and the sine of the angle between them. So how do we determine the direction? We have to use our cross product. So that cross product, we use the right-hand rule. Our right-hand rule, since it's V crossed B, one version of using it, or one method, is to point our fingers of our right hand in the direction of our velocity vector, and we curl our fingers through the short angle towards our magnetic field vector, and our right thumb will then point in the direction of the force on a positive charge when Q is positive. If Q is negative, our thumb's going to point in the opposite direction of the force, so our force will point in the opposite direction of our thumb when we're doing our right-hand rule. So we have to be careful whether Q is positive or Q is negative. Alternatively, we could use the left-hand rule and point our left hand in the direction of the velocity vector and curl that in the direction of the magnetic field, and our left thumb would point in the direction of the magnetic force on a negative charge. But we'll stick to talking about the right-hand rule, and that if we have a negative charge, well, the negative means 180 degrees, so 180 degrees of up, in this case, is down. This is the y direction, positive y to negative y. And then our b and v vector then are in our xz plane. Another way to look at the right-hand rule is using our thumb and index finger. If we point our index finger in the direction of the point our index finger in the direction of the velocity vector, if the charge is positive, we'll point it in the opposite direction of the velocity vector if the charge is negative. So we point our index finger in the direction of our QV and point our middle finger in the direction of the magnetic field. In this case, our magnetic field is out of the page. Then our right thumb will point in the direction of the force. So that's another way that sometimes is easier to do than curling your hand. And yet a third method of applying the right-hand rule with our right hand is to point our thumb again in the direction of the movement of positive charge, which will be the opposite direction of the movement of negative charge, opposite being 180 degrees. And then we point our fingers in the direction of the magnetic field. That way the plane of our hand is in the plane of the velocity vector and the magnetic field vector, and our right palm will then point in the direction of the force on the positive charge. So we have three ways to apply this right-hand rule. This right-hand rule just gives us the direction of the magnetic force. The magnitude of the magnetic force we can still find by magnitude of FB will be the charge that's moving through the magnetic field, and we multiply that by the velocity that it's moving, and sine phi, where phi is the angle, the short angle between the velocity and the magnetic field. So here we just use all magnitudes. If the charge is negative, we let the charge, we actually use the absolute value of that charge because we're just getting the magnitude of the magnetic force. So if we look at this example, here we have three situations in which a charged particle has the same velocity, but it's traveling through a magnetic field, B. So we have our direction of magnetic field and the direction of velocity on a Cartesian coordinate system, a three-dimensional Cartesian coordinate system. So we want to know what's the direction of the force on the particle. So my favorite method is to use the right-hand curl. So I would point my right hand, I would point my fingers of my right hand in the direction of my velocity vector, and I'd curl them. When I curl them, I'm moving them down in this direction, and my thumb then is going to point, here's my thumb pointing out there by my hand, it's going to point in the positive z direction. So here, the solution is here's our magnetic force, FD, will be in the positive z direction. Here we also have our velocity vector and magnetic field vector. They're perpendicular to each other. That doesn't have to be the case, but it's always true that our magnetic force will be perpendicular to both the velocity vector and the magnetic field vector. So if we can identify the plane, in this case, the plane in which our velocity vector and our magnetic field vector lie is in the xy plane. So our magnetic force is in the positive z direction. The only other alternative would be the negative z direction. If we had a negative charge here, if this was negative instead of positive, in that case our magnetic force would be pointing in the negative z direction. So let's look at example B. In example B, we do have a negative charge. We have our velocity vector, we have the charge moving in the negative y direction, and our magnetic field pointing in the negative z direction. Again, the velocity and the magnetic field are perpendicular to one another. So now if we use our right-hand curl is going to point our thumb, right, a big old thumb, it's going to end up pointing in this direction. When we do that right-hand curl, curling V into B with our right hand. However, since it's negative, that's going to put our magnetic force in the negative x direction. Third example here is where our velocity vector is pointing in the negative y direction, our magnetic field vector in the positive y direction. Well, we could certainly try to do a right-hand curl here. We could try to curl V into B, which is the short angle. We have 180 degrees or negative 180 degrees. In fact, here our velocity vector and magnetic field vector are anti-parallel. They're in opposite directions. So in this case, our magnetic force is equal to 0, so we won't draw the vector on this page. So practice with this problem, practice using all three methods for the right-hand rule, and see if you can find one that really works for you and makes sense. Again, in class, my go-to is this curling your right hand fingers in the direction, pointing them in the direction of the velocity vector, curling into the direction of the magnetic field, and find the direction that your thumb points. But it's nice to have other methods available to you. We'll look at another example in the next video. We'll do some more analysis of magnitude of magnetic field and what happens if the velocity vector and magnetic field vector are not at 90-degree angles, but that angle phi is something less than 90 degrees.